In this video, we will look at Newton's three laws of motion. The first law states that in an inertial frame of reference, an isolated body will be in a state of uniform motion unless acted upon by a force. If it is at rest, it will remain at rest. If it moves with a constant velocity, that is straight line motion, with constant speed, it will continue with a constant velocity. It is often misunderstood that Newton's first law follows from his second. People reason that, well, F equals ma, if F is 0, then A is 0, and the velocity is constant. However, this chain of reasoning is incorrect and misunderstands what Newton's first law implies. The first law basically tells us that inertial reference frames exist in nature. And then it tells us how to identify inertial reference frames. You identify them by observing the behavior of isolated bodies. If an isolated body with no forces acting on it is at rest and remains at rest, then you are in an inertial frame. If, however, you notice that this isolated body starts accelerating, then you know that your frame of reference is non-inertial. So the first law defines inertial frames of reference and states that they can be found in nature. Newton's second and third laws are dependent on this existence of an inertial reference frame. If you are in a non-inertial reference frame, Newton's laws do not hold. We continue with Newton's second law. The second law states that in an inertial frame, the net force acting on an object, that is, the sum of all the forces acting on it, is equal to the rate of change of momentum, where momentum, denoted by the letter P, is mass times velocity. We will look at a few simplified cases first. So, for a point object of constant mass, since the mass is constant, we can take it outside of the derivative, and this simplifies to m times dv over dt, but the rate of change of velocity is just acceleration, and so we have the more familiar form F net equals ma. Notice that this is F net, not just F. What are the implications of this second law? And for that matter, what is a force? Well, we can first attempt to define forces operationally. We know, for example, that a force can be exerted by a stretched rubber band or a stretched spring. Even without knowing the details of Hooke's law, we can somewhat confidently state that if you stretch a spring a certain amount, a fixed amount each time, then if you repeat the amount of stretch, it will repeat the amount of force exerted. So let us use this instance of a force, a repeatable, quantifiable force, and see how that affects various objects. What we find, if we look at a single force acting in two different cases on two different test masses, is that a1x over a2x is equal to m2 over m1. That is, the acceleration of the object is inversely proportional to its mass. Rearranging this, we get that m1 a1x is equal to m2 a2x. We applied the same force separately on two different objects, and we found that their masses and accelerations were related in this manner. Now that we have this relation, we can identify this quantity ma with F. Furthermore, since acceleration is a vector, we expect that force itself will be a vector. And so we can quantify the force exerted in an interaction by mass times the acceleration vector. And this gives us the force vector for that single force. However, this does not end our story of the second law. When multiple forces act on a single object, we say that the net force, the net resulting force of all those individual interactions, is simply the sum of those forces added as vectors add. So our identification of force as a vector has important properties, because it tells us how those forces add. They add the same way that vectors do. That is, forces obey linear superposition. That is, the effect of the net force is the same as taking the effects of each individual force and adding them all up. This is not a trivial observation. For example, in optics, you would have seen that shining light through each slit individually does not give the same effect as shining them through both at the same time. You cannot simply add up the patterns that you get. Instead, you get interference. This is a consequence of the fact that the intensity of the light goes as the square of the amplitude of the electric field. In other words, there is a difference between adding the electric fields and then squaring them, or squaring the electric fields and then adding them. That is an example where linear superposition fails. But what we are saying is that forces do obey linear superposition, and they add as vectors do. And so we get that the net force acting on an object is equal to the sum of the forces, and this result will create a single acceleration, and the mass times that acceleration is equal to the net force. Or, reverting back even further, this net force is equal to the rate of change of the momentum of the object. So in an inertial frame, the net force acting on a body is equal to the rate of change of its momentum. We also note that if this net force is zero, that tells us that this derivative is zero. Or in other words, if the net force on a system is zero, the momentum of the system is constant, or we say conserved, because it is constant in time. We end with the third law. Newton's third law states that for two objects A and B, the force of A on B is equal to the negative of the force of B on A. Note that these are both vector quantities. It is sometimes stated as all forces occur in pairs. For every action, there is an equal and opposite reaction. However, this statement is a little confusing because it implies that one occurs before the other, when in fact they both occur simultaneously. So, in general, other than colloquially, we don't like to use this expression. There are some hidden implications in the third law. The most important is that all forces are caused by interactions between two systems. Since these two systems are interacting, that is, they act on each other, you have a force of A on B and a force of B on A. And thus, no force occurs in isolation. If we are observing an object and we see that it suddenly starts to accelerate, there must be a cause which can be detected by a corresponding force on some other system. So the third law states that nothing occurs in isolation. Every effect that we see has a corresponding paired interaction occurring on another system. We remember from the second law that if the net force is zero, the momentum is constant. And this provides us with some further insight into the third law. Consider a system which is made up of two objects, 1 and 2. So the total momentum, and momentum is also a vector, is the sum of the individual momentum vectors, p1 plus p2. If the system is isolated, then the initial momentum is equal to the final momentum. And so P1 initial plus P2 initial is equal to P1 final plus P2 final. We rearrange these to get the object 1 terms on one side and the object 2 terms on the other side. And we recognize that this is equal to the change in object's 1 momentum here, and on this side we have the negative of the change in object 2's momentum. Now this interaction with each other, right, what happened here is that they interacted with each other and exchanged some momentum. They exerted impulses on each other. Well, this takes place over some period of time, so we can divide both sides by delta t, and then take the limit as delta t shrinks to 0, so that these become derivatives. And so we find that the negative of the force of 1 on 2 is equal to the force of 2 on 1.